Okay, so after we all got our exercise walking up the stairs, well, I've received during the week a couple of emails asking about the exam. So let's make a few points clear. First of all, the exam is with open material. What do I mean? Anything printed you can bring with you. No devices, unfortunately, because I can't cut you off from the internet and it's supposed to be your exam. Okay, so print whatever you think is useful for you. Just a caveat, I've seen in previous years students coming with 2 meters of stacks and spending the whole exam trying to find something in it. So if you're bringing something, familiarize yourself with it so it will be useful and not just a waste of time. An exam is not the point where you start reading the relevant chapter in the book or trying to find a solution that you think you have seen somewhere. Okay, so that also covers questions about page with information. You can bring full books, so whatever works for you. Okay, then the second question is, give us exams from previous years. I've put what I had handy in Lemida, Lambda, whatever it's called, the exams of last year with full solutions. For some reason I haven't yet found exams from a couple of years ago. I'll try to locate it, but in any case, just in order to prepare yourself for the exam, it's better to spend most of the time going over the lectures, solutions, and doing all kinds of exercises cute after you have read the material. Just to sit and solve previous exams in the hopes that you'll get some small permutation of questions there. Hopefully it won't happen because I'm trying to write exams that are a bit different for each year. So it's always nice to try to apply what you have learned, but it's not, most of you are doing Begrut or somewhere close to doing Begrut. It's not a Begrut. It's not that you solve the 4 given permutations of a question and you're prepared. Okay, any other questions? Okay, so let's go on, and what we're doing today is we start from writing down how you add angular momentum and or spin, and from that we'll get to a point of how do you write down a many particle Hilbert space, and from there we'll get to interesting questions about modern physics like entanglement. Okay, so let's start from the simplest system we know, one particle with spin half. Now I don't care at all about the position. Let's say it sits on a specific position, or I'm not interested in knowing anything about its position or energy or whatever. Okay, as usual in physics, the first thing I do, as is usual in quantum mechanics at least, I write down the Hilbert space. What do I mean? I check what are the possible results of a measurement here. what do I measure? Here I measure the spin. I don't have anything else to measure once I killed all spatial or momentum information. Okay, so basically I can get here a result which is either up or down, or if you want, plus minus 1, or some people write it as plus minus half, and whatever, if you want to put in units, plus minus half h bar. Okay, so the main thing is the size of the Hilbert space is 2. Well, I could take here a different system. Let's say a spin 1. Okay, for a spin 1 particle, we measure either up or 0 or down, or plus minus h bar or 0. And so on and so forth. Just as an agreement for the continuation of this lecture, and there are many different notations on how to write it down. So the first term is the s squared, like L squared, and the second term is the n over sz. So basically in this notation I'm writing s and sz. Perhaps it's better. So I choose an axis in which I perform the measurement and write down the wave function. Here I would have s equal 1, sz equal and it's basically the same notation. Okay, and I can develop it for larger and larger spins. Okay. Now we'll start to do something a bit more interesting. Just before that, so I have a particle with S and Sz. What is the value of S for a spin half particle? Or better perhaps to write it down as a square. Remember the mapping So what is L squared? We remember that it's basically so here at Sz we have the values of plus minus h bar over 2. And here, what are the possible values? Wasn't a rhetorical question. I want you to think about it and come up with an answer.
Which the L with S.
Right. So what will be the answer?
H bar squared LS או open סוגריים LS ועוד אחד.
So it's L here is S here it's half. L plus 1 is 3 halves. And this is 3/4 h squared. So this is the total spin of the magnitude of the spin in this problem of 1. Okay. So let's leave it for a moment. 2 particles. So, how do I approach it? There are 2 different ways to approach it. One is on the SZ component of the first and second particle. We're still here dealing with distinguishable particles. Okay, the other way is to try to build our Hilbert space for the total spin. Both of them give the same results, but we approach it in a different way. Okay, let's start from my point of view with the more intuitive way. And that's simply writing down the states as for example, let me bring them consistently both up. Okay, these are the possible states that we can have along SZ for each one of the particles. What is the size of the Hilbert space? 4. Of course, because for the first particle we had a Hilbert space of size 2, the second one has a size 2, and any possible configuration is possible. So it's 2 times 2, 4. So the size of the Hilbert space is equal 4. Sometimes in order to save, to make the notation a bit less cumbersome and to save writing, we'll simply write the 4 states in the following way. Okay. So far so good, rather trivial. The interesting thing that you see out of it, if I'll do it for n particles, I'll have 2 to the power n states. That is a big problem with solving many particle physics on classical computers. Very quickly, the size of your Hilbert space grows into sizes that you can't just map on your computer. Today, it's possible, perhaps on a good classical supercomputer, to do problems with 2 to the power 24, 26. So the maximums that you can solve is 26 particles. If you build these states on a quantum computer, well, they're building nowadays something with 100 qubits, and you could fool yourself to say, well, I can do the problems of size 2 to the power 100. Unfortunately, they lose coherence quite quickly, and although in principle you could have put 100 particles, you can't solve it on today's hardware. One of the solutions is to put in some error correction protocols. Perhaps some of you have run into it in the popular press or whatever. But these error correcting algorithms required hundreds or thousands of quantum bits for each virtual bit that you're running on your computer. Again, not something that you can do nowadays. But perhaps with some hardware and error correction progress, it will become a bit more doable. Anyway, that's one way that I'm doing. I said I could look at it from the other way. If we would have been doing here classical physics, I would be able to say that these are 2 vectors. I add them in any angle between them, and I get a whole continuum of results that are possible. But we're doing here quantum physics. And in quantum physics, S can, of a half plus a half, can be either 1 or 0. Can't have anything else. Remember, it's S squared, so it's 1 minus 1. It's the same squared as 1. So how many states will I have here? Well, I can write down no other states. Fortunately, if I'm very good in arithmetics, I can see it's 4. That must be because I'm describing the same system, but in other notation. In one case, I'm looking what happens on the z direction for each particle. On the other case, I'm looking on the total spin and the total projection on the z direction. But the size of the Hilbert space should not depend on the basis that I insist using. Which one is a better notation? Depends on the problem you want to solve. If you can measure each particle by itself, of course this is better. Let's say when we're doing quantum algorithms, that we'll do in the next lecture, you usually address each particle or each bit by itself. So there's this type of notation makes sense. If I'm going and putting a magnetic field on the whole system, makes much more sense to look on this case. Okay. Since these are two bases, in principle, I should be able to translate from one base to a second base. What does that mean? I should be able to present a state here as a linear combination of states here, and vice versa. That's a translation from one basis to another basis in any quantum system. How do we do it? Well, there's something called Clebsch-Gordon coefficients. In the good old days, I would always get a question Flash-Gordon coefficients, but nowadays no one knows who's Flash-Gordon. Okay, I'm right. and we'll see how it's built. But in such simple cases, we can get a lot of intuition just from looking on what's happening here. Let's see. I have here 4 states. If you are so unfortunate as to speak with your chemistry counterparts, they'll immediately jump up and say, these are the singlet states, these are the triplet states. A lot of the chemistry of molecules and atoms comes on from looking on transitions, and even quantum optics comes from looking at transitions between singlet states and triplet states. The reason for the name is clear. 1, 3. Okay, but let's look on what we have here. Total magnetic moment in the z direction minus h bar. What does it mean? If I'm looking on the single particles, I'm sure that both particles point down, because no other way that I can get as total as z equal minus h bar from summing up the 2 spins. This will give you 0, this will give you 0, this will give you 1. So, without doing any calculation, I know that this guy, okay, this is a minus, goes here. This guy goes here. So the Clebsch-Gordon coefficients are just 1 in this case. 1, that's that. Life becomes more complicated for these 2 cases, because the total spin SZ1 plus SZ2 in both cases are 0. And how do I know if it corresponds to the singlet state, which always SZ is equal 0, or to one of the states of the triplet? Here we have to start to do a calculation. Okay, so I'll start actually from giving the result and then proving it. Okay, I'll write it here. In a moment, I'll start to prove it. But what does it tell me? It tells me that it's a different linear combination of the states appearing here with one spin up and one spin down. Now you can come and tell me this state doesn't make any sense. Why is the first particle up? When it's up, it's a plus sign, and when it's down, is a minus sign. What breaks symmetry?
Oh, it means it's depends on how you put the axis, if it's going up or down.
No, it's even simpler. It doesn't depend on the axis at all. And definitely from the physics point of view, there can't be any difference between putting the first particle up and the second down and the second down and first up.
It doesn't even matter because you need to square it anyway if you want to get any measurement.
You can always multiply here by a -1. It won't change anything. You could multiply it by any phase e to the power I5 and it won't matter at all. So it's just a convention to write this plus and this minus meaningless. Doesn't make any difference. Okay. So I need some space, so I'll erase this guy because okay, let's put down just information from here. So I have the whole information that I had here. Okay. So let's prove the results that I've written here. So I'm writing down what's S squared. Okay. Can't argue with it because that's the definition of S. Total spin of the first one plus the total spin of the second. Okay, what are the pluses and minuses there? The pluses and minuses as we have defined in one of the previous lectures. Okay, you see why it's true, or you want me to elaborate?
I can't really see it.
Excuse me?
I can't really see
Okay, let's write down. Okay, this term's nothing to write. Okay, let me rewrite this term in a different way and see. Agree with this statement? That's just scalar multiplication of two vectors. Okay, so the first term I just copied. The second term, I'll have anytime I multiply S1, whatever plus or minus, with S2. So I have these two terms, so I have S1x, S2x. Right? And with the i's and the plus and the minus, the same is correct for S1y, S2y. And why did I do this rather unclear transformation? Because when I'm working with S1x and S2x, I'm not working in the natural basis that I'm trying to do the calculation, where I have S squared and SZ. Sx and Sy are hard. But these are all three components here are well defined in this basis. Because plus will just move it up, minus will just move it down. So life is easy. So that's the reason I went from this representation to this one. Okay. So, I'll clear up a bit of space. Okay, I just wrote down explicitly both states s equals 0 and as s equal 1. What do I expect to get here? For the plus case, I'm supposed to get two h squared, because for s equal 1, it's L times L plus 1h squared. And for the 0 case, meaning the minus here, I'm supposed to get 0. Something bothering you?
I'll get it in a
No, it's just I'm checking whether the expectation value of this wave function gives me 0. It has to give me 0 because it's an s equals 0 state. And in this state, it's an s equal 1, so the expectation value is 2h bar squared. That's it. So I'm checking it to save me rewriting it for the plus and minus each time, so I'm writing here just plus minus. So, okay, that's not 2, that's s. Okay, for the ugly algebra part of the lesson, here we go. Okay, I have here a quarter before everything. Oh, you should have shot me. So, square root of 2. So here I have just half. Good. Okay. S1, S2 plus 2S1Z, S2Z don't change the wave function when I operate on them, right? They just pull out a number. So the first 3 terms, it's just the multiplication of this guy with this guy or this guy with this guy. No cross terms there, because cross will be orthogonal and won't contribute to anything. Okay. First 2 terms as trivial as they exist, right? That's the total spin of the first one, total spin of the second one, Okay, if it's a plus, so all these contributions, if I have a plus here and plus there, will be h bar squared over 2, and I have it twice. I have it twice here and between the two parts. If it's minus, so if I'm multiplying one of them with a plus and one of them with a minus, I get the minus sign. Okay. So before we dive into the mathematics of the Clebsch-Gordon coefficients in general, here we did it for the simplest case and actually guessed the result. I would like to spend a bit time on the states because this became a very important concept in physics, which is entanglement. So, like many good things in physics, this started from a thought experiment suggested by Einstein in actually 1935. So that's the famous EPR thought experiment, which was performed in the lab, I think it was 2 years ago or last year. Nobel Prizes to people who actually performed this experiment were given. Okay, so EPR, Einstein, Podolsky, Rosen. Rosen actually was a professor for many years in the Technion and was a student of Einstein. Also, Podolsky, I'm not sure if it was a student, but a collaborator of Einstein. So what is this experiment? Starts from the following thought experiment. Let's say I have two spin half particles sitting in the lab whatever. Now I go and do the following protocol. I put a magnetic field on them. Okay. What will happen if I put a magnetic field on them? If it's in the singlet state, nothing. If it's in this state, nothing. If it's in this or this state, it will either go in the direction or anti the direction of the applied magnetic field. So I know that my total SZ is 0. Then, for some reason, one of the particles goes right and the other one goes left. Okay, so I know that the wave function is actually there are cases where I can even decide that it's in a singlet, but it doesn't matter for this particular experiment. Okay, I know it's in this state. Now, one of the particles goes to the, want your right or my right? Okay, let's say right and okay, do I know what's the spin of the right going particle? No, it could be up or down. Do I know what's the spin of the left one? No, it could be up and down. Now, the famous names that we borrowed from actually communication engineering. We have here information, Alice and Bob. Two experimentalist setting, one on Earth, one in Alpha Centauri. Huge difference between them. Now, Alice goes and measures the particle and measures up. If Alice measures up, Bob necessarily measures down, because if it's here in up, the other component is down. Now, when does it happen? Immediately. Because all this happened in Hilbert space. No structure, no time, no anything. So, I'm paraphrasing and it's not exact, but problems with relativity can't be. Or non-locality. I do something here, it immediately affects me there. Now, what I described at the moment is, although sometimes in popular journals or popular presentations, is described as the problem. This is not, actually this is not a problem at all, because I can explain it even on a classical level. What do I mean? Let's say you have you draw just two pairs of socks, a red one and a green one. And you're known to sometimes get mixed up and wear an unmatching pair. And now okay, you're an astronaut, you wear your socks in the morning, jump on your spacecraft and go to heaven knows where. Now I'm asking someone who's left on Earth, what type of socks is the astronaut wearing? You can go to the drawer and check what is left there. If 2 are red socks, I know he wore the green socks, and so on and so forth. So the fact that if I know what's happening here, I know what's happening here is not surprising. I can have also classical correlations. The point is that it's something more, and that's known as the Bell inequality. And it's built on the fact that a wave function has more information than saying just Sz is up or down for each particle. This is a complete description of the Hilbert space. Meaning I can go on and ask questions on Sx and Sy. Now, I don't want to spend here time on going through the mathematics, although it's not really complicated. But the point is, let Bob or Alice do an additional measurement. Let's say that after they measured the spin in the z direction, they go and measure it in some angle to the z direction. From all we know about quantum mechanics, the fact that they measured it in the z direction, if Bob measured the second particle, it cancelled out this probability, this part of the wave function. And then I can build up protocols of experiment which will give results that can't be described classically. There's no way that I'm going and what actually is the requirement for a classical measurement? For a classical measurement, I require that when the 2 particles were together at the beginning, they sat down and gave a table of what value one particle will show if the other particle is in a different value. So they have to have an infinite size table. If I'll measure it at 27 degrees, you will say up and you will say down. If you measure it in 47, you will say up, you will say down. On the other hand, here basically every measurement deletes part of the wave function that doesn't correspond to it. And the order of measurements makes a difference. And what Bell has shown mathematically is that you can't write it down as such a table. So if you can't write it down as such a table, and nevertheless in the experiment you get the quantum mechanical result, you have to agree that the whole game is played in Hilbert space, and quantum mechanics is the description of nature. Now, Einstein was very unhappy with it because it tells you that our reality is not relevant. Everything happens in Hilbert space. Now, measurements shows that he's wrong. So what do you do with it? Some people say, okay, that's the true description of nature is only the Hilbert space. Whatever we see around us is some projection out of it that we construct, but there's nothing very fundamental about space and time and everything else. It's just everything that happens in Hilbert space. Other people say something like, look, hidden variables, these tables don't work. But non-local hidden variables do work. Now, there's a lot of different ways how to create a non-local behavior. One of the most intriguing but still far out explanations is, oh, no problems, there's all kinds of wormholes going through nature, and therefore it's okay that it's non-local because no one can explain you how it communicates through a wormhole, what does it really solve, but nevertheless people are happy with it. And most physicists just revert to the good old shut up and calculate. We know to tell you exactly how this experiment will end up, and therefore we're happy. We know how to operate with our quantum mechanics. Is it local? Is it non-local? Are there hidden variables? Aren't? Is everything just everything happening only in Hilbert space, and that's all or not? We don't care. We go and do our calculation, and since until now no smoking gun experiment has even a suggestion for it, came out with, if you'll do this and measure this, this interpretation is right or not. So at the point we are still stuck. And this up to points where people say, and not just some far out crazy people like Penrose and Gerard Dehouf, one of the people who developed the quantum field theory and got a Nobel, both of them are Nobel, say, well, quantum mechanics can't be true. Nevertheless, it works beautifully. So that's what we have at the moment, and after the break, we'll go back to some more hard calculations of calculating showing how the Clebsch-Gordon coefficients are calculated.
Richard.
Yeah.
Schrodinger equation famously doesn't work with relativity. Do we get the same issue with Taurat or with the Klein-Gordon equations?
Yeah. This is not dependent on the equation. I didn't put here a Hamiltonian. I didn't say anything on the development of time. It told you that the development in time goes left and right, since I'm not talking about the position, degrees of freedom. I don't do with it anything. I'm talking only on the degrees of freedom of spin up and spin down, which I said don't develop in time, therefore they're not as true. I don't need any equation to describe not developing in time.
It's just the idea of Hilbert space.
You can tell me, and you're right in it, but here is the wave, what is the measurement and how does it collapse the wave function? And it's deeply connected to that, but not to the description of how it develops in time. Because there I break down completely the development in time.
It's not just about developing in time. If I understand correctly, you get, especially when it comes to spin, with the Dirac equation, you get that if you travel faster, there are some things that cancel out. So this is not the solution.
So we want to limit ourselves to spin or angular momentum. As a general notation, we'll look on the case of two particles. And we have particle 1, which has J1 and M1, and particle 2 says J2 and M2. Okay, J could be any integer or half integer number. So the first particle has J1 of 5/2, and second particle has J2 of 1. Principle can be any combination. Okay. So in this case, basically, we have a basis of M1 and M2. If we choose to describe it as the SZ component for each particle, same as we did for the half case. And in this case, we have J and M. As usual, you already should be familiar with it. Everything that we do has to do with commutation relations between operators. Okay, that's the good old familiar commutation relation between any two components of angular momentum and also spin. Not surprising. Okay, here. Same is for 2. What happens if I commute an operator that works on two different particles, J1 X and J2 Z, for example? They don't commute. Sorry, they commute. They don't care about each other. That's a very important result, correct for everything in many particle physics. If I measure for particle 1 something in the x direction, it doesn't influence necessarily what happens to particle 2 in the z direction.
Even if I and the J are the same.
Yes. Well, first of all, if I and j are the same, we know that it's equal to 0 even for the same particle. Commutation relation between two identical operators is always 0. But the point here, and it's a point worth considering for a moment. You can come and tell me, well, you just before the break gave us an example of the EPR experiment where you said that if you measure particle 1 in the z direction, it determines particle 2 in the z direction. But that's not a property of the operator. It's a property of a special state given there. It's not a general property of the operators. What I'm writing down here is commutation relation for any. If you'll recall what we did, let's say for x and p, what did we say there? The commutation relation between x and px is larger or equal to h bar over 2. What does it mean? If I have a particular state, I can get any value, but this value must be larger than h bar over 2. Here what I'm saying is, I can get any value, but I don't have a limit how small it is. It could be 0 if I prepare the wave function correctly. Could get here a value that's not 0, depending. But that is a lower bound on what is the best case that I can get. And the best case between two particles could be a wave function where the correlation is 0. So it's a bit delicate, but it's important to distinguish between these two statements. I can have a state where the commutation, or if I measure one, it has influence on the other. But I could have a state where there's no connection. On the other hand, let's say for x and p for the same particle, I can't come up with a state where x doesn't influence p and vice versa. Okay, some additional state connections, commutations. Why is that? Because here we replaced the z component of the full J if we are choosing to work in the basis of the combination of both angular momentums or spins, then I don't know what happens to a particular z component of a particular particle. All of it you can prove according to what we have already defined. Okay, so these are our tools. What do we want to accomplish here? If something is given as Jn, we want to present it as a linear combination of the bases M1, M2. That is our goal here. We want to create a connection between the two bases. How do I, in general, achieve it? I achieve it by the same method that I always do translation between two bases. And perhaps the most compact way to say it is I multiply it by 1. Well, how do I do the multiplication by 1? In the following way. We have shown somewhere in the beginning of the course that this is the projection operator, and if we sum up over all basis states, it's 1. So I can always multiply by the projection operator over the whole base. And that's the most general way that I go from one basis to other. Why? Because now I'm left here with the basis vectors, and these are the amplitudes. This is the number. So if I know to calculate this amplitude, this scalar multiplication between two vectors, I finish. It's true for any transition from any base to any base. Just write down the base you're interested to move into as a projection sum over projection operators, which is 1. You're always allowed to do it. Just multiply it with the older representation, the vector control representation. You know exactly how to transit from one to another. Okay. So, what I'm doing here is very similar conceptually to what I did for harmonic oscillator and for other problems angular momentum. I find some anchor, some value that I know, and by ladder operations move from there. So what was the state that I knew in the previous examples that I did for the 2 spin half case? What was the case that it was a no-brainer to write down the relation?
Plus and this minus.
No, that was hard. We had to do a calculation.
Both up, both down.
Yeah, exactly. That is the point. Meaning that if I know that m is equal to m1 plus m2, life is easy. So writing it down explicitly, okay, if I subtract an operator that pulls out the z component of m1 in this case and of m2 from the z component of the combined one, it has to be 0. Just for this case, I'm looking on a specific case here. It's not a general case here. Can multiply it by m1 and 2 to the left. Now it becomes very clear because remember these guys are Hermitian. So I can operate with them to the left or to the right. So this guy, it's easier to operate on this guy, and we'll get here n. This guy we will operate to the left. So, what did I learn from it? A very important thing, which we knew previously, actually, but now I proved it mathematically. I have to get here a result of 0, right? If m is equal m1 plus m2, this is 0 and this can have any value. Yeah, because a 0 times whatever value is still 0. But if they are not equal 0, this must be 0. So I know that all components for which m is not equal m1 plus m2, the amplitude is 0. Actually, it's trivial almost. We used it in the previous case. So we know the maximum point. So that's one piece of information that we're using. Okay, what else do we know? So that's first point, second point. J of the combined system must be either, has to be larger than the difference between them in absolute value and smaller than their addition. Okay, for example, if J1 is equal 3 and J2 is equal half, J will have the values or 7/2 or 5/2. No other values are acceptable here.
Why not 6? I like 3.
Why not 6?
Why,
No, not
like
6. You want to ask 3.
Yeah, 3.
Because it has to jump in jumps of 1. That we have proven.
Oh, okay.
It can start with a half or a whole or an integer, but the jumps are always of 1. Between half and minus half, you're not going to 0. You're going half and minus half. 3/2, half, minus half. Oh, minus 3. You can't be. re-emphasized it, but I'm writing it again. And how do I know it? Well, it's reasonable, but let's write it down mathematically. Okay, the size is always 2j plus 1. So if I have two particles, it's 2j1 plus 1 multiplied by 2j2 plus 1. Now, if I'm looking on this basis, the Jn, so n write it down simpler. And this is a problem in summation of series, simple one, and you'll end up okay, so that's just proving the statement, which is very logical. this is almost a trivial statement because any transition between bases is a unitarian matrix. Someone can tell me why? We talked about it, I think, in one of the first lectures. What does a unitarian transformation mean?
That when we will take the lie vector with it, we get it's a a cross of the vector.
Even simpler, it just doesn't change the length of the vector. A unitarian transformation preserves length.
Oh, because
And since every state here is length 1 by normalization, and if I'm transferring between two bases, I have to preserve the normalization. So that's correct for any transformation between bases. If you write a transformation between bases that is not unitarian, you made a mistake. Why it can be written as real, I'll not prove it here, but any phase you can pull out and it has no influence. Just you multiply everything by the same phase and then put your additional phases. Okay. If n1 and n2 are bases, on orthonormal basis, what is the scalar multiplication between n1, n2, and n1, n2 prime?
Zero? No.
A good old friend, Kroneker's delta. If they are equal, it's 1. If not, it's 0. So what can I pull out as a conclusion? Okay, why is that true?
Somewhere Jm equals 1.
Right, I just multiplied it by 1. For what is it good? If I know one of the connections, I can know something about the second amplitude. And we can do it the other way around. for the same reason. Again, just Unitarian. And I could sum up on, instead of this guy, on J and M in this. It's not two summations, it's either this or this. Because I'm transferring from one basis to the other. Okay, so how do we play our game? We try to build some recursions between states. How do I do it? Okay, so I wrote the same expression, but either in the basis of Jm or in the basis of M1. And use the corresponding operators, either J or J1 plus J2. Okay, what does a plus minus do? Change m as plus minus 1 and gives me some normalization factor. We did it a couple of lectures ago when we were doing angular momentum. Same thing I can do here. So it seems that we took an ugly expression and made it even more ugly. I'm multiplying it with a particular state M1 prime. And sorry, here I forgot to write the summation. Okay, let's look what happens to this expression. Okay, for here nothing special happens for the left side. just move this to here. Forget something? No. Okay, the other guy, because of the delta function, forces me to take only one component of the summation here. The delta will kill all other components. So what do I get here? I get just yeah, now I'll do something that's perhaps nowadays with a tablet you can do it easy. M prime is just a notation. I can write just M instead of it. So just so what did I get from this whole game? I basically got a relation between between three amplitudes. Yes, this guy and this guy. All of them multiplied by Jn. So if I know one or two of them, or one or two of them are killed by the plus minuses here, if I get 0 here, I can determine what happens. So basically, for J plus if I look on a diagram in the M1 and M2 space, I get a connection between M1 and M2 and M1 minus 1 M2 and M1 M2 minus 1. That's what's written here. For the J minus, okay, so how do I use these connections? Let's do a, I don't want to do a full example, we'll do a few points there. Let's look on the connections between a particle with J1 equal 1 and J2 equal half. So how many states I have for the for these guys? Okay, M1 can take minus 1, 0, and 1. J2 can take, M2 will take plus minus half, 6 states. Okay, just a slight extension of what we did with the two particles half. What are the possible J's? J could get a value of half and a value of 3 halves. Okay, so here I have M can take values of plus minus half. Here, so I have 2 states here. M can take here values of plus minus 3 halves and plus minus half, 4 states. Right, so 6 states in any representation. So, what do we know? We have to take What? And connect it with states. Okay, so these are the two bases that I can present them in. Two states I know the Klebsch-Gordan amplitudes immediately. These are the maximal states. So let's do one of the triangles. So I'm looking on this amplitude. Well, I'm looking on the j equal 3/2 and actually let me do it this way, sorry. Okay, so you remember we had the structure of one where I remove here plus minus m1s and m2s, and here I just remove m. Plus m can I do here? No, because I'm at maximum. So I have only the minus component here. So I know that my two states here will be what happens here? Pluses I can't push any higher, right? just minuses. So once I have -1 for here, and once I have 1 and -1 for here, which is -half. All I have to fill up is a normalization. Those ugly states that we have written before. So this is 1 times 3 square root. This is, sorry, this is what do I know? I know that this guy is so I got a connection between those two guys, which tells me something about how this guy splits between the 0 and half and 1 and -half, whereas these two guys. Both of them are possible because M here is just the summation. Both. So I have two amplitudes that I don't know, and some arithmetic connection between them. Let's go to another case. So there I'll get the following connections. What is this guy?
That's something we already solved.
It can't be. I can't have J0, and so I can't add to half 1. I can add to 0, 1, but I can't add to half 1. So this is not relevant. So I have one connection between this guy, which appears here. I have a second connection. What is this guy? That's one. Our good old friend.
Okay.
So I know the connection here, I know the connection here. I finished one of the connections in the bases. So I ended up with okay, just from what appears here. Okay. Now, either one spends a long and think what happens with 3 and 4 particles. You need 3 particles for quarks. So it's long, ugly calculations, but you can get the connections between the 2 bases. In the good old days, you could have recognized a particle physicist. There was booklets with Clebsch-Gordon coefficients, and he would have one of them in his pocket. Nowadays, just Google Clebsch-Gordon coefficients, you'll get the whole structure for quite large values of angular momentum and for numbers of 3, 4, 5 particles. Is it fun? No, but the idea is very clear. You just go and do the recursions and connect between all the coefficients, and it's doable. Is it worth doing? Well, if you need it, yes. Nowadays, you just pull it out from tables that you have everywhere in the internet. Okay, so that's about addition of angular momentum. The important thing to remember here is basically you can present a system with more than one particle, either S1Z, S2Z, S3Z, S4Z, and so on and so forth, or the total spin and the M corresponding to this total spin. What is more convenient depends on the problem. If you want to describe, let's say, a proton which has always total moment of half, it would be easier instead of writing down the 3 moments of half, 0, 3, let's say, plus half, minus half, minus half for the 3 quarks. It's easier just to write the J and M of the whole proton. Other problems, which we will see in the next lecture, which will talk about quantum algorithms for quantum computers, would be easier to use actually J1Z, J2Z, J3Z, and so on and so forth. So depends on the problem. But you know now, at least in principle, how to transfer from one representation to another, and it's only a question of representation. Okay, we'll stop here.